Hello and welcome to our Exam 2 practice problems. So I normally don't have a review week like I do this semester, so this is a great chance to review some of the chapters before Exam 2. So what I have here for you now is an Exam 2 practice problems. So it's a couple questions from each chapter just to kind of get you back in the swing, because it's been a while since we've done like chapter 6 and binomial distributions, and moving forward all the way to chapter 10. And with our exam coming up, I wanted to have this for you. So I think this is a better practice with all of them in one kind of setting. This is kind of a very simple way to practice and get used to doing some of the stuff that we've been doing and practicing with the formulas. So I'm going to go relatively quick through this, because if I spend a lot of time on this, we could be here for another hour just going over these practice problems. So I am assuming and making the assumption that you have at least read the problem and have attempted these problems prior to watching the video. If you haven't, you can still watch it, but I'm going to go pretty quickly. I'm not going to read every question to you and then go through it. I'm just going to go into things that you should be looking for, how to set problems up, and talking a little bit about them, but I'm not going to go in-depth reading over everything. I'm going to assume that you've read the problem prior to. So you can always read the problem, pause the video, read the problem, and then attempt it, and then watch the video. That's one good way to do it if you like. There'll probably be a couple of videos of this. I'm not exactly sure how many yet, but this will be broken up into at least 2, maybe 3 videos, depending on how quickly I go through them. All right, so let's get started. So for our practice problems, the very first 3 questions here are going to be from chapter 6. So we're going to be talking about binomial distributions here. A couple ways we can test out binomial distributions to understand what we're doing. So when we have a binomial distribution, remember, binomial distribution, the bi part is for a success or failure. So the very first one, we're talking about Greek life organization, and we're looking at binge drinking among Greek life members. And we're given a prevalence rate of 34%. So we know this is 0.34. So one thing always do on the side, if we're given a prevalence rate, that is our probability of people binge drinking in Greek life. So our P is equal to 0.34. And we have a sample size of 10 students. So we know our N is equal to 10. Highly recommend always writing the stuff on the side so it's easier to find what's going on later. So then part A is, what is the expected number of response from the sample that will be binge drinkers? So keywords here, expected number, right? So either you're a binge drinker or you're not a binge drinker in Greek life. So if you are or not, a success or failure. So this is going to be our binomial distribution. When we see expected number in the binomial distribution, our formula is N times P equals mu. Well, on the side here, we already have our N and P laid out for us. So it's N is 10 times 0.34, which equals 3.4. So our average that we expect to see from this is 3.4 students that are part of Greek life that binge drink. Part B, the probability of finding 4 binge drinkers in the sample. So what is the probability of actually finding 4 individuals in the sample? So we have 4 here. So 4 is a value that we're trying to find. If we're trying to find a value, the value is X is equal to 4 binge drinkers. So now we have to put our binomial distribution formula to find out the probability of X equaling 4. So we write that as the probability of X equaling 4 is NC of X to the P to the X power times Q to the N minus X. Once again, we have P and X already over here on the side, and we have an X value, so we just need to do Q. Well, Q, once again, is equal to 1 minus P, right? P is the probability of success, Q is the probability of failure. Them together will sum to 1, so 1 minus P is Q. So Q, in our situation, is going to equal 0.66. Now, we write all this out, so it'd be 10, choose 4. How many different ways can we choose these 4 individuals from our sample of 10? Multiply by our probability of success, so 0.34 to the 4th power, multiplied by our probability of failure, 0.66 to the N minus X, so it's going to be 10 minus 4, which is going to be 6. Don't put 10 minus 4 in the calculator for an exponent, just solve for that one. Unless you're going to put your parentheses right in there. You're going to not have a good answer if you do it that way. Once again, I always like to solve things step by step, so I would do 10 choose 4, put that in the calculator. You'll see it, in the calculator, we always write it as NC of X, and the calculator is going to say NCR. Same thing, your calculator, you put a value of N, pick the choose function, put your value of X or R as the rate, and you'll get your choose function. And when you do that, you'll get 210. You can also do it long way by doing the factorial method, whatever you find more convenient for you. And then that's going to be multiplied by 0.0133 times 0.0826, which then is going to give you a value of 0.2307. So that is your answer. So what is the probability of finding 4 binge drinkers in this sample? And that's 0.2307 or 23.07%. Moving on to number 2, like I said, it's another binomial distribution. This one we're looking at the prevalence of asthma with children. So either they have asthma or they don't have asthma. So I think the tricky part here that I've seen from some students is that when we collect a sample, and we have a sample of 12 children were interviewed, so these 12 children are our sample, that's N is 12. And then out of those 12 children, 4 of them reported to have asthma. So X is 4 here because that's how many we had. Now the very first part you might say, well, what's the expected number? So when we do expected number, remember that's N times P equals mu. Anytime you see expected number, expected value, think of the mean, the mu. So N times P, or off over here too, to the side, P is equal to 0.17. So N is 12, P is 0.17. Multiply those out, and it equals 2.04. That is your mu. Now then part B is what is the probability associated with the findings of the research team. So the research found 4 of them. So what is the probability associated with finding these 4 children out of the 12 with the prevalence being at 17%? So plug this into our formula. So we're going to do our choose function. How many different ways can we pick these 4 children out of 12? Our p-value of 0.17 to the 4th and 0.83 to the 8th. Remember that the exponents at the very top here, I'm going to erase that because it looks horrible, but when you look at these exponents are going to equal the value of n, because it's the probability of success to the probability of failure among this total population. So these exponents always are going to equal to a value of n. So 4 plus 8 equals 12, so we know we are good there. I think it erased something else here. Let's see. 0.7 and 0.83 to the 8th power. Once again, I do this step by step, so I do our choose function first. So 495, 0.17 to the 4th. Now you're going to get a very small number. Recommend doing scientific notation for this, because you're going to get 8.352 times 10 to the negative 4th. You can write that out longhand, but make sure you have a value. Don't just put zeros there. If you put a lot of zeros, if you multiply anything by 0, you're going to get 0, so don't do that. So scientific notation here will surely help. And then we're going to multiply 0.83 to the 8th power, and you're going to get 0.2252. Multiply all this out together, you can get a value of 0.0931. Can you put this all in the calculator just as this way? And yes, you can. Sometimes you might get a value that's a little bit off than if you just go out certain values. The more decimals you go out, the more accurate it's going to be if you plug it all in. Don't worry, make sure as long as your work on your piece of paper for the exam is there and I can follow it, you're going to be fine. All right, so moving on to number 3, which is our other binomial distribution problem. So here, let's write out we'll be fine. Remember, so this one's looking at sleep apnea among elderly. So we're having a sample of 16 elderly people, so that's our N, where we have estimated disease, we're set to 0.19, so that's our probability. And then our X here, so they had 16 elderly and 11 reported a confirmed diagnosis of sleep apnea. So So there's our X value here for when we're answering part A, because that's how many people they found in this report. And so first part was the probability associated with this finding. So we have our N, P, and X. The only thing we have to do is get our Q, which is the probability of failure. So it's 1 minus P. And when we do that, our Q is going to equal 0.81. Now we plug this all into our formula. Once again, remember I'm going quickly because I assume everybody has at least looked at this problem and attempted it. And I'll be going over the parts and just to make sure you have a great understanding of what we're doing. So we have 16 choose 11. How many different ways can you choose 11 people out of the 16? Times our probability to the x power times q to the n minus x. Once again, I write it all out. It's fine if you don't. If you write it all out, you get 4, 3, 6, 8. Choose function, then 1.6. Oh, I'm sorry. Going a little quick. 1.164 times 10 to the negative 8th. Make sure you watch this. If you're on a calculator, this will look like this. It'll have an E, negative 8. The E is scientific notation telling you it's times 10 to the negative 8, or you move the decimal 8 places to the left. And then 0.81 to the 5th power is going to give you 0.3486. So we're going to multiply these all out, and when you do that, you're going to get a very low number, 1.7724 times 10 to the negative 5th. Now, this is a big point here. Don't put 0.0000 because that's assuming that there's a 0% probability. I mean, there's a very small chance that this is happening, but there's a very small chance that you find 11 of these confirmed sleep apnea people in the sample size of 16, right? It's a very small chance you find it, but there is a chance you can find it, right? So we don't want to just say it's 0.000 because that's assumed 0. You want to at least get that 1 in there, right? Because if we're to the negative 5th, there's going to be 4 zeros before the 1. So this is a really good answer in scientific notation. This one is okay because you're at least showing me that there is a probability. It's very small. It's not as accurate as this one, but if you just left it 0.000, that to me you're saying there's a 0% chance of that happening, and in fact there is a possibility that that can happen. Part B is the expected number. Anytime you see expected number, it's mu. Remember mu is going to equal n times p here. Just look for our n, 16, times the probability, 0.19. Multiply those out, 3.04. And then part C, the only thing we're doing now is we're updating it. So we determined that, it's actually 0.27 is the more updated prevalence statistic. So now our n stays the same, our x is staying the same, but our probability is now changing to 0.27, and our q is now also going to change too since our probability changed. So 1 minus p will give us our new q, and that's going to be 0.73. So now we're going to, with this new updated prevalence statistics, put it in our problem. So we're going to have 16 choose 11, 0.27 probability of success to the 11th power times the probability of failure to the 5th. Write it all out. This is still the same. So remember, if you're using the same part in multiple spots, if you already do it, you don't have to do it twice. You can just use what information you already know. This value is going to be also very low, 5.559 times 10 to the negative 7th times 0.2073. You're going to get a value of 5.033 times 10 to the negative 4th. But once again, hold on. Once again, this is a very good answer. If you were to write 0.1235, right, this is also a good answer. It's not as accurate as this one, but at the same time, you're telling me it's not a 0% probability. All right, so that's all the time I got for this video. I will see you all on the next one.